a highly intelligent father, an average child. This is not unusual. It happens in millions of families worldwide. Sometimes a grandfather was brilliant, the father average, and the grandchild exceptional. What is the pattern? Intelligence is not like eye color or height. It is a complex system, not a single gene or trait. Three systems: genetic inheritance, epigenetic regulation, and the environment, all interact to shape intelligence. Every scene in this video connects to the same story. From DNA to the womb, to childhood, to the brain. Genes are sections of DNA that carry instructions for building proteins, the materials of the body and brain. More than 1,000 genes contribute to intelligence, each with a tiny individual effect. No single genius gene exists. Each parent contributes 50% of their genes, but which specific genes pass to the child is entirely random. A brilliant father gives only half his genes to his child. The other half comes from the mother. A genius father has many intelligence-related genes, but which of his genes actually pass to the child is random chance. Some intelligence-related genes are dominant, some recessive. A brilliant father may carry genes that stay hidden in the child. Intelligence is polygenic, meaning it results from many small gene contributions working together, not one controlling gene. Extremely intelligent people are outliers. Their children, on average, will be smarter than average, but closer to the mean. Francis Galton studied thousands of families and found that extraordinary parents produce less extraordinary children, on average. Heritability of intelligence is estimated at 50 to 80%. The rest is explained by environment, not genes alone. Epigenetic studies changes in gene expression, not the DNA sequence itself, but whether genes are turned on or off. A father's diet, stress levels, exercise, and habits alter the epigenetic tags on his sperm before conception. When sperm meets egg, the embryo undergoes epigenetic reprogramming. Most paternal marks are wiped clean. A small number of epigenetic tags survive the reset, particularly those related to stress, diet, and trauma. Studies show that stressed fathers, through epigenetic sperm changes, produce offspring with altered stress responses. A father's nutrition in the weeks before conception affects folate levels in sperm, influencing the child's neural development. Some epigenetic changes pass not just to children, but to grandchildren, creating multi-generational inheritance patterns. Swedish research showed that grandfathers' food availability affected their grandson's health and lifespan through epigenetics. Most critical brain architecture, neurons, connections, cortical layers, forms during pregnancy, shaped by the mother's environment. Folate, iodine, omega-3, and iron during pregnancy directly build the child's neural architecture, not the father's DNA alone. Chronic maternal stress floods the fetus with cortisol, altering the developing brain stress system permanently. After birth, 80% of adult brain connections form by age 3. The primary caregiver's responsiveness wires this development. Fathers who actively engage with children during early years positively affect language, problem solving, and emotional regulation. Many intelligence-related genes are on the X chromosome. Boys get their X from the mother, meaning maternal genes dominate in sons. Daughters receive one X from each parent. Both contribute equally to X-linked intelligence genes in girls. In childhood, environment explains more variance in IQ. By adulthood, genetic factors explain 80%, the reverse of childhood. The brain's cognitive capacity is constructed through experience, learning, stimulation, and environment, not delivered by genes. Children who hear millions of words in the first 3 years develop significantly stronger cognitive foundations. Even with exceptional genetics, a child in an intellectually barren environment will not develop their full potential. Children from lower socioeconomic backgrounds show lower IQ scores, not because of genes, but because of environment. Average IQ scores rose 3 points per decade for 100 years. Genes did not change. Nutrition, education, and complexity did. Adopted children raised in enriched environments show significantly higher IQ than biological siblings in poorer conditions. Unstructured play activates problem solving, creativity, emotional regulation, and social cognition simultaneously. During deep sleep, the brain consolidates the day's learning, prunes unused connections, and strengthens new ones. Iodine deficiency alone reduces IQ by 10 to 15 points permanently. Nutrition is a prerequisite for any genetic potential. If intelligence is so valuable, why didn't evolution create a simple direct inheritance path? The answer is adaptive. Random genetic variation between offspring means some will survive new threats that others cannot. Uniformity is fatal. Ancient groups needed different cognitive types: spatial hunters, social connectors, memory specialists, creative problem solvers. Intelligence-promoting genes spread through the group, not just direct offspring, supporting cousins, siblings, and tribe members. Female ancestors who invested more in child brain development passed on more intelligent offspring, creating a maternal bias in intelligence transmission. Intelligent behavior, creativity, humor, eloquence evolved partly as display signals for mate selection, not just for cognitive function. The brain uses 20% of body energy. Evolution would not maintain this cost if intelligence did not provide massive adaptive advantages. Post-reproductive grandmothers who taught grandchildren extended intelligence transmission beyond direct parent-child inheritance. Children who believe intelligence can grow through effort actually develop more cognitive capacity than those who believe it is fixed. Teachers who expect more from students, regardless of actual ability, produce students who achieve significantly more. In low-income environments, genetic factors explain very little variance in IQ. Environment overwhelms genetics. A securely attached child explores more, learns more, and develops greater cognitive capacity than an anxious child. Growing up, bilingual strengthens working memory, attention, and cognitive flexibility, regardless of genetic background. Regular aerobic exercise raises BDNF, brain-derived neurotrophic factor, which promotes neuron growth regardless of genetics. Genes define the channel. Environment, nutrition, stimulation, relationships, and challenge determines the river's depth and flow. Statistical regression, random gene shuffling, epigenetic reset, and environment together explain this universal pattern. No intelligence test at birth can predict adult cognitive outcome. Potential is always in process, never complete. Fathers transmit 50% of their genes. Epigenetic marks from lifestyle, behavioral modeling, intellectual environment, and values. A father who reads, discusses ideas, challenges thinking, and models curiosity creates a cognitive environment that builds the child's brain. A father who improves diet, reduces stress, and exercises before conception can positively modify sperm epigenetics. The greatest gift a father can give is not his genes. It is curiosity, environment, challenge, warmth, and time. Each new child is not bound by their father's intelligence. They are a new possibility, shaped by the world they are given. Genes and environment are not competing forces. They interact continuously, inseparably, and beautifully to build every mind. The more we understand intelligence, the more we realize it is not owned, fixed, or inherited. It is grown, built, and shared. Responsive caregiving, language richness, emotional security, and intellectual stimulation build any child's intelligence, regardless of genetics. Before birth, before school, before play. The mother's body is already the child's first and most powerful learning environment. Unlike height or eye color, intelligence can be significantly modified by environment, making it uniquely improvable. Neuroplasticity, the brain's ability to rewire, continues throughout life. Intelligence can grow at any age with the right conditions. The intellectual legacy a father leaves is not in his genes. It is in the environment, habits, and values he creates around his child. A father's intelligence does not transfer directly, but his care, presence, and environment build what genes alone never could.